Well, good. All right. So thank you everybody for coming to our BOSNOG. First up, sponsor plug. Thank you to Rakuten and Cumulus. Big shout out to Hannah from Rakuten, and definitely Katie and Becky from Cumulus, and of course Pete from Cumulus for joining us tonight. If you want to hear about either Rakuten or Cumulus, you can talk to me about Rakuten or Pete or any of the others from Cumulus about that. So the BOSNOG state of the group address, we'll call it. Yeah, so this is our 8th event. Pete pretty much came up with the idea in 2015. What's the matter? Oh, okay. We started this in September 2015. That was our first meetup. It was at my former stomping grounds of Microsoft Nerd Center, and we had, I think, Big Switch present. It was pretty cool. But since then, we've doubled our attendance since that first meetup, so we've been making a lot of progress and gaining momentum. We have over 300 members now. I think the last meetup that we had in the summer was with the New England Peering Forum, and that was kind of a joint venture, and it really, I think, increased our exposure. A lot more people joined. But we do have a Slack. I'd recommend that everybody that's here go ahead and go to that website there. You can get onto our Slack. We have a Twitter account that we don't use, but hey, we got one, right? It exists. And then the third point here is we could use some help. Pete decided to go move into LA for some reason. I'm not sure why. Ethan is usually pretty busy with his new thing. And we got a bunch of other people that are just not around that we could use some help. So even if you want to do a talk, that would be great. If you want to help organize, if you want to sponsor an event, please let me know. I'm pretty responsive on Slack, so that's your best way to get a hold of me. All right, so let's make networking great again, right, guys? So, so we're gonna do a bit of a roundtable thing. Pete's gonna use his fancy iPad whiteboard thing, but I think it would be good for us to just kind of grease the skids on what exactly we're going to be kind of trying to cover today. So I put a few slides together just because Pete was too lazy to. So, it's super true. So I think a lot of us that have been involved in networking for the last 10 or 15 years are pretty familiar with the traditional networking model. I call it the Cisco model that we all grew up with, whatever. You got your core distribution access model, is that spanning tree fun. You've got links being blocked. You've got unused bandwidth, layer 3 routing, ACLs at the distribution layer, all that fun stuff. So I think a lot of people are familiar with this. But what we're trying to talk about today is we really want to talk about some of these new designs, and you'll hear the words CLOS and spine leaf a lot. But I think even just that alone has some new interesting challenges. So the spine leaf network and CLOS model, so most people working in the data center networking side of things are familiar with this model. Pete will talk about it some more, but typically you're doing layer 3 instead of layer 2 in between all the different layers in the network. We're kind of relying more on routing protocols instead of, say, spanning tree or any kind of multi-chassis lag trickery, I'll call it, where you're kind of bridging switches together and making one big logical switch. There's a lot of different stages or different types. Pete will get into that. But one of the big things is, the east-west traffic over the last, I would say, 5 or 7 years with virtualization, big data workloads. A lot of that east-west traffic is increasing. So you're seeing a lot more of that and less of the north-south. So these are the things to start to think about as we go through some of these talks that Pete's going to help us with today. And the other thing that I think is important to mention is overlays, especially VXLAN, are becoming more and more popular ways to deal with providing that layer 2 that people might have been used to, or applications that needed that. It's just another way to do it, but where a lot of people are running like routed fabrics at the bottom layer and the spine leaf interlinks, and then they're doing things like VXLAN over on top of that. So some of the things that I would recommend you guys start thinking about as Pete going through his talk is, you know, how do we scale these things? Where do we do VXLAN termination, right? So there's people doing VXLAN termination at the leaf or the top of rack, you know, with the hardware-based switch. There's people doing it at the server, or they're doing it in, say, a VM. But in general, I think that I see, you know, this side of the world of networking progressing and moving towards like a network-based virtualization, you know, running on top of a very simplified fabric to just get packets from A to B. So Pete's going to do some magic whiteboard time. These are the 3 things that he and I discussed a couple weeks ago. He tends to just kind of go with the flow, which is great. So if you have anything in mind in particular, certainly add to it. But the 3 things that we kind of talked about, Pete and I, was scaling, availability zones. We kind of put this up on the meetup. You know, chassis. When do you use chassis-based switches? How do you overcome and deal with 32-port spines? You know, where, you know, how do you scale past that? Layer 2, layer 3. So Pete's a proponent of, you know, free-range routing. Now it's on mute. Whatever. Hello? Yeah. And then, you know, layer 2, layer 3, the free. So Cumulus loves this routing on the host thing, and I think that a lot of people have been using. I've used it in my past experiences at Microsoft. I've actually used it here at Rakuten for certain applications, actually Kentic. So I know there's some people from Kentic here. We used Quagga to actually advertise and Anycast our Kentic agent. So I think routing on the host is wicked awesome. And then VXLAN can solve some problems around multi-tenancy and micro-segmentation. So Pete will talk about that, some different ideas. I'll hand it over to Pete. Thank you guys for coming.
All right, thanks. Thanks, James. And I really can't stress this enough. I'm making this up as I go along, so if you've got ideas, let me hear them. Check, check. All right, looking good.
Put it higher up or turn him up.
Check, check. All right. So the first thing I'll say is if somebody here is in the Network to Code Slack, you should send a link to the video stream. Somebody might be interested, just saying. We can expand the community. And I'll pile on to what James said about asking for help. You know, I think the stories of operators, and I say this as a vendor, the stories of operators are extremely important and poorly understood. And I think the biggest thing out there, and hopefully we'll expose a little bit of this tonight in our discussion, is everybody's got exactly the same problems. You think your technical deck is unique, and you think that this other company is doing it right, and you think that you have these unique problems and these unique disasters and tire fires, and it turns out that your problems are exactly everybody else's problems. And we start to solve these problems and really kind of move forward as an industry by talking about it. It's effectively group therapy. So whatever it is that you are working on is probably worth having a discussion about. So we're always looking for speakers. From a sponsorship standpoint, I mean, we're really just looking for somebody to buy beer and pizza. So it's not that expensive, but it's hard to do when you're funding it out of pocket. So if you're recruiting, if you're looking for folks, anything like that, it's a great opportunity for some low-cost advertising. And then organization, I've fully and completely abandoned James, so he could use some help here. So with all that said, For those of you who don't know me, I'm Pete Lumbis. I'm a technical marketing engineer at Cumulus. I'm a CCIE routing and switching. I'm also a CCDE, or the Cisco Certified Design Expert. My background, I spent about 5 years in the Cisco TAC working in routing protocols, so supporting Bgp, MPLS, multicast, on everything that isn't XR. If it had an IP address, it was my problem. I was part of the global escalation team, so I was one of the 4-person team that globally was the last line of support in TAC. If you had to talk to me, you were having a bad day. Through the course of working in TAC, when I did the CCDE, I was one of the first 100 people in the world to do the design expert exam, and I was the first person in the Cisco support organization to do it. And it's funny that I figured out how to do network design by working in TAC and seeing every wrong way to design a network. There was literally a question on the exam where they showed me 5 topology diagrams, and I was like, well, I've had cases on 4 of these, so it must be the other one. So I've been at Cumulus about 3 years. I come from that same traditional networking background, CLI, routing protocols, spanning tree, layer 2, layer 3, not Linux, not a system admin. I did not know what an Ansible was before I started. I'd not even read Ender's Game to know that reference. Or if you got deep nerd cred, the Ursula Le Guin novels to know that. So I learned all that along the way. So what we're doing at Cumulus that's a little different, and how this kind of relates to our design roundtable, is we look at the switch as not being significantly different than the server. So we run on whitebox switches, which have Broadcom ASICs and Mellanox Spectrum ASICs. And so you're looking at basically the same kind of things that are in most of the Nexus lines and most of the Juniper QFXs, and basically everything Arista produces. So that's same packets performance, same packets per second performance, same number of routes, same number of ACLs, same everything from that perspective. It's just changing how you consume that hardware. So you can go and buy it from Dell, from HP, from Mellanox, from EdgeCore, a few others, whoever you want to do business with. And then us at Cumulus as software, we look at the world as, well, what's special about the network? And what's special about the network is the networking, not the operations. Meaning, we make the switch look like a 48-port Linux server. So we're a pure Linux distro. So I can use all the same tooling, the same configuration, the same automation, the same monitoring, the same everything as my compute side. And really what this is, and the reason why I'm giving you this little sales pitch, is because when it comes to network design and network architecture, to me, we're trying to blend the operations of networking from all of this learning of compute. But what compute sucks at is networking. So why can't we turn that upside down and start to make compute understand some of our learnings from networking? So why can't we do things like routing on the host and actually have a server peer with BGP instead of doing MLAG and bonding? Why can't I use EVPN out of the server? Why can't I have the server generate multicast packets instead of having my top-of-rack switch do it? When does it make sense to do some of these things? And so we really look at this world a little bit differently and say, how do we blend it? How do we make the network do what the network's good at? And how do we make servers do what the server's good at? So the first thing I'm going to talk about before I basically start badgering you with questions is that architectural design that James talked about. You know, it all starts with the leaf and spine, also sometimes called the CLOS. And for those that are curious, a CLOS, a CLOS, is named after Charles CLOS, who was an engineer in Bell Labs, was inventing telco switches. It's not an acronym, it's a name. So when you write it, big C, little L, little O, little S. So the spine and leaf network, the CLOS network, I blame Jim for that one. What you're going to do is you're going to connect your leaves to all your spines. And you're not going to interconnect the spines, and you will probably connect 2 leaves together in a pair for your top-of-rack pair. And so now all traffic between racks is 1 hop away. So I'm going to go up and back down to get between those racks. The big thing about the spine and leaf network is this scale out. So as I go across my spine, I can scale out this architecture. So if I need additional bandwidth, I can add additional spines. As I roll out racks of compute, I can just roll out more leaves. And so it becomes simple building blocks that we can piece together to build this architecture. The thing that really enables this, you'll notice here I have 5 spines in my diagram. What contrasts this to the design that we're used to, where I put 2 giant Nexus 7000s or Nexus 9Ks, you know, big 13-slot chassis in my core, is I put a pair of them, and I use them in MLAG and VPC. And there shall only ever be 2. It's like the networking Sith. They always travel in pairs. And, well, that sucks, because then I'm going to lose 50% of my bandwidth. Or what if I run out of ports? Or what if I need more bandwidth? I don't have any options. And so it turns out to be just as evil as the Sith in that way. And so what I want to do is I want to use routing and layer 3 across this fabric, this simple end-to-end basic connectivity. And by using layer 3 here, I can use equal cost multipath, Ecmp, to load share that traffic across all of the spines. So the first thing that's going to come to mind is that sounds great for a routed environment, but I've got a 200-year-old mainframe that requires a layer 2 heartbeat between them. And so for that kind of solution, we look at something like EVPN and VXLAN to solve that, which allows me to do layer 2, layer 3, and multi-tenancy. So I can do layer 2 extension between my racks over that L3 fabric. And I can load share that traffic across all those spines while still allowing those L2 applications to cluster or providing tenant isolation at L2 or L3. So I'm going to pause there. Questions? Don't be shy. I see you twitching.
Is there anyone here that's currently using this type of policy right now in their data center?
So like less than 10%. That is neither surprising nor unsurprising. I think everybody in the industry is, I mean, it's really a journey. So I'm talking to customers all the time, and I'm at a lot of these kinds of events. And this is what I mean. Like, you're like, oh, I don't want to raise my hand because I'm not doing this. Well, guess what? Like, most of the hands didn't go up here tonight, right? Everybody's kind of figuring out those same problems. So, I just got a softball. I swear to God that wasn't a setup. So the question was, is there a maximum number of leafs that are supported? So in most of these switches that you're seeing out in the marketplace today that are not chassis, and I'll talk about chassis in a second, they are 48-port leafs, so 48 server ports, and 32-port spines. And so what that means is I have a 32-port spine here, and I have a 48-port leaf at the bottom. So I can support 48 servers and 32 leafs. And if I have 2 leafs in every rack, that's 16 racks. So at the simplest, the answer is 16, right? Because I'm going to have to connect a server port down to every leaf. I'm sorry, a spine port down to every leaf. So once I fill that spine, I'm done. The first step that you can do is you can step down the bandwidth to increase the port count. So usually what are done are 40 gig ports here or 100 gig. What I can do here is I can get that same amount of bandwidth. So in this case, we'll say it's 300 gig ports. And I can break those, each 100 gig port into 4 25 gig ports. Or I can break each 40 gig port into 4 10 gig ports. And now I can double the number of ports on that switch. And so I can go from 32 to, anyone? Bueller? Something like, 128. Plus or minus, some chips have limitations where they can't support 128. But effectively, I turn that 32 ports of 100 gig into 128 ports of 25 gig. The engineering trade-off, because everything is a trade-off, is that where I only needed 3 uplinks before, I now need 6 uplinks. Sorry, 4 times as many, 12 uplinks. Because as I'm cutting that bandwidth down per link, I need to increase the number of links. So I'm consuming fewer ports on the spine but more ports on the leaf. And we have a couple of customers doing that where they have, say, 16 spines all running at 10 gig in order to get 100 racks or so out of a single 32-port spine. To go beyond that, you can do what's called a 3-stage or a 5-way CLOS. And what that is I have leaves, I have spines, and then I have super spines, super duper spines. And it's built exactly the same way. So I have a spine and leaf network. Generally, we would call these pods. The super spine is sometimes called an interpod spine. And just like a leaf, it's going to connect to every super spine. So I connect my pod spine to every super spine through all the pods. And so now I can scale this out. Out of 1 RU switches, I can easily get roughly, what's the number off the top of my head? I think it's somewhere in the million. I mean, you really start to have cabling challenges, but you can easily hit something like 1 million server ports connected to leaves here.
Going back to the 3-stage CLOS, you were talking about 32 ports of spine fixed. You don't have to use a fixed switch. You could use a chassis already.
Yep. So the question is, could I use a chassis in that as an alternative? And Ethan, in his wisdom, is blowing up my spot. I'm gonna get to that in just a second, and I'll talk about chassis and chassis options. Any other questions before we keep going forward? So I'm continuing to answer your question. So this allows me to scale up. So now this here is a 32-port device. This is a 32-port device. So I can support roughly 32 of these pods. Right? So it's pretty big scale out. The challenge, though, is what are my ports on these spines? Right? How am I managing this over subscription? Because the reality, if I back up and clean this up a little bit, the reality here is that I have to dedicate half of the ports of my spines south and half of them north, because I don't want any packet loss in those spines anywhere in that fabric. I always want to manage my oversubscription at the leaf layer. And so what that means is I have to come in here, and for a 32-port device, I have to have 16 ports down and 16 ports up. How I decide if I want to put 2 ports into one switch or have 16 super spines is up to me. But I effectively have to take half of my bandwidth and use it up and half of it down. So this sucks. We do have some customers doing this, but it can be a huge cabling challenge. And so this is where customers start to look at chassis to do this. And what chassis do is they effectively abstract out this part of the network. That spine, super spine combination becomes your chassis. Whether it's an open networking chassis that I'll talk about in a second, or an Arista or a Cisco chassis, they're all spine and leaf networks wrapped in a piece of sheet metal. So what that means is on a chassis like that, I'm going to have line cards and a line card ASIC, and I'm going to have fabric cards, and those fabric cards have ASICs. And they're actually going to do something internally to do that forwarding as if it was a spine and leaf network. So I actually have this little CLOS network inside my chassis. The question, though, is what does that CLOS look like, and what do I have visibility into? So for most of these, this whole thing, this whole thing is literally a black box. I can't look into it, I can't see it, I can't troubleshoot it. That's when you call TAC and they start doing ELAM captures. That's where they're trying to figure out what's the fabric point of exit, what forwarding engine is it hitting, all of those terrible nightmare scenarios. So this is what a chassis buys me, is it wraps up all that complexity from the configuring of BGP to the cabling to all of that in a piece of sheet metal so I don't see it. And then they're running something internally to provide an ECMP environment, a chassis. But at its core, it's the same exact fundamental concept. One thing that's been new in this area is Facebook released something called the Facebook Backpack. There's another device out there from a company called EdgeCore, a whitebox switch manufacturer, called the OMP 800 and the OMP 1600, which are, the Backpack is a 4-slot chassis. The OMP 800 is 8 and the 16 is 16-slot chassis, 13 slots, something like that, real big. And they do the exact same thing. But what they're doing that's different is, again, I have a line card, and I have fabric cards, and there are ASICs on each of these, and it's spine and leaf. But what they're doing that's different is they're actually building it out of the exact same components of 1RU switches. So for an Arista chassis or a Cisco chassis, Broadcom or any other vendor are going to make special chips that are designed to be chassis chips. They effectively do the same thing, but they do some different things around buffering and queuing and things like that to make sure that they can what's called arbitrate packets across the backplane and figure out when to send. So you have an Ethernet network with this box thing in the middle, this CIS chassis, and inside of that CIS chassis is something that's not Ethernet, is not standard. And so what Facebook has done in their backpack design and EdgeCore in their OMP 800 design is this is an Ethernet chassis. So they're using the exact same 32-port 100 gig switch ASIC for a line card and the exact same 32-port 100 gig switch ASIC for a fabric card, and they're running BGP and Ethernet across this backplane. And as I mentioned earlier, these are 32-port line cards. But how do I have 32 ports if this is a 32 by 100 gig ASIC? What they actually do is they cut the line card in half, and they put 2 ASICs on every line card. And to take it a step further, in that traditional chassis, you have a supervisor module or a pair of supervisor modules, because CIS always travel in pairs. This is my, like, I just came up with this. This is my new favorite thing. I hate chassis. You have a pair of supervisor modules, and that one CPU on one of those active supervisor modules is controlling the whole thing. So I have a 256-port chassis. I have 256 BGP peers, all terminating on that same CPU and contending for that same CPU and memory resources. In this chassis, in this open networking chassis, what's actually different is that each of these ASICs also has a CPU. And each of these ASICs runs its own individual piece of software. There's actually 4 fabric cards in the Facebook Backpack. And this architecture, this design, they're all online through the Open Compute project, OCP. You can find them online and learn a bunch of information about it. But what this means now is that I actually have 16 ports down being controlled by that ASIC, and I have 16 ports up. And as I said, I'm running eBGP through that fabric that's all wrapped in a piece of sheet metal. There are no exposed ports on those fabric ASICs. They're a fabric like any other fabric in a chassis. But what's super cool about this is, number one, I now only have 32 ports being driven by a CPU. Right? I have the ports that belong to this ASIC being driven by that ASIC CPU. So if I have a 256-port chassis, any CPU in that chassis is only driving 32 ports and dealing with 32 peering. So the scale is pretty cool. The other thing is, if I look inside this chassis and I do like a show IP route on this ASIC, I actually see 16 ECMP routes into my fabric because I'm doing BGP peering. And then I can log into my fabric ASIC and I can do a show IP route on a fabric ASIC. And I can see, oh, I've got ECMP paths out my front panel ports. I can take it a step further and I can actually span one of these ports because they're all Ethernet. And I can actually start to monitor with something on box like a Telegraph or a Sensu or a Prometheus, each of those fabric and line card ASICs and CPUs. So I can sit and collect and graph the counters of the fabric module itself. And so that's the one thing that the open networking is doing that's a little bit different than your traditional Cisco or Arista chassis where it is closed like that. Any questions about that? All right. So one of the other questions that comes up a lot when we talk about routing is, what are the routing protocols I should use in the data center, and how do I, what should I actually build out that spine and leaf network out of? Should I use OSPF? Should I use ISIS? Should I use BGP? So in those conversations, I'll say one of the largest networks in the world is using OSPF, and they are like the only person I know running OSPF at scale like that outside of a service provider. I still don't understand why they picked OSPF. I'm not naming names on purpose. Somebody does it. But almost everybody is kind of rallied around BGP. A lot of that comes from the fact that Microsoft and now Facebook wrote an RFC that's pretty easy to read about BGP in the data center, how to operationalize it, what do your autonomous system numbers look like. You know, we all think of BGP as being the service provider protocol, but it's just a routing protocol like anything else. And so as a result, a lot of folks have gathered towards that. But what's super annoying is, again, in that spine and leaf network, as I come in, if I'm going to do BGP, I have to not only assign autonomous system numbers, and we'll talk about that in a second, but I have to build BGP peerings with IP addresses on each of these links. I have to manually define the IP addresses on those links. I have to manually define who's my neighbor on the other side of that link. And I have to manually define what is the autonomous system number of the device on the end of that link. And so the administrative overhead of configuring this is high, and trying to automate this is a nightmare. And so one of the things that we've seen companies like Cisco have been pushing ISIS as the solution for this. And so instead of running eBGP, they're suggesting running ISIS within that fabric. And what's the advantage of that is ISIS doesn't rely on IP, so I can build this entire fabric without IP addresses, and everything will just come up and it's magic. And that works, and it works well. And if you just need connectivity, I think it's a great solution. What Cumulus has done is we took RFC 5549, which is the ability to advertise IPv4 routes over an IPv6 BGP session. And so what we do is we use IPv6 link local addresses on the interfaces that are automatically generated by the device. We then build a BGP peer to whatever we hear sending IPv6 router advertisements on the other end of that link. And we become BGP peers and exchange v4 and v6 routes over it. And so now I get that same IP-free fabric, just like ISIS gives me, but with BGP. And before I tell you why that's better than ISIS, any questions about that? And so one of the things I want to show you is, not only are we managing the IP addresses, but we're also managing the autonomous system numbers. So we've made that easier to say, look, eBGP and iBGP are only about rules. It has nothing to do with what messages I send or anything like that. It has a lot more to do with how I determine where to send route advertisements and how I intend to set the next hop of the routes that I'm sending. So what Cumulus did to take that a step further was not only make it so I don't have to have IPs on those interfaces, but I don't need to know the autonomous system number. So I can say something like, neighbor, Ethernet 1, remote AS, external. And that's my BGP configuration for the device for that port. And now, if I think about how I'm generally going to cable up a top-of-rack switch, I have a block of ports on every top-of-rack switch that are my uplinks. And so every top-of-rack switch is going to get that exact same configuration that I can now copy and paste, hopefully through automation to get there. But we can even eliminate the need to coordinate those ASNs. So going back, again, the push for ISIS is about making it so you have an unnumbered fabric. It's about not having to manually do all this IP address management and burn like a /24 worth of IPs just for your infrastructure links. So once I do eBGP unnumbered, I don't need that anymore. So the next question is, why eBGP over ISIS? And why eBGP over iBGP? And that's where EVPN comes in. And the reason EVPN matters is EVPN is going to allow me to do L2 over this L3 fabric. It's going to allow me to do L3 over that L3 fabric. And it's going to allow me to do multi-tenancy over this L3 fabric. If you're familiar with L3 VPN, it is identical from a concept to L3 VPN and how it functions like that. And so just like L3 VPN, what I'm going to do between my leaves is I have to build IBGP peerings to exchange this EVPN information, which are generally MAC addresses and MAC plus IP information about the hosts that are attached to me. So I have an ISIS fabric. I want to run EVPN over it. So I configure IBGP. Well, that's great. Now I have a full mesh problem where every leaf needs to be a peer of every other leaf. And that sucks. Well, you go, haha, I remember that class that I took that one time where we solved this problem. I know how to fix this. We're going to use, you got it, route reflectors. So what I've done, I've built ISIS everywhere. I don't want to run IBGP in a full mesh, so I'm going to use route reflectors. And so instead, I build peerings with IBGP up to all my spines. So I just configured ISIS everywhere, just so that I could then configure IBGP to all those exact same devices to do exactly the same thing. Now I'm running two protocols for what? And so my opinion on this whole thing is that the ISIS component is stupid and unnecessary. I have some opinions, if you haven't noticed. I sometimes like to share them. So get rid of ISIS entirely, and then just run eBGP here. I don't need route reflectors anymore. And then I'm going to exchange my IPv4, IPv6, and EVPN information exactly the same as I would in an IBGP scenario. And so now I have one protocol that looks the same absolutely everywhere, operates the same, configures the same, troubleshoots the same. And that's not unique to Cumulus. I would actually advise this for anybody building an EVPN network. We're just going to make it easier for you. Questions, thoughts, comments? Oh man, that's like the best. Y'all are on fire. Like I feel like there was a bowl of questions. You know, I'll just pick the questions out that I was expecting. So the question was, what is ASN assignment in this kind of eBGP spine and leaf network? So my first recommendation, to make another plug, we really need a shorter company name. There's a book called Bgp in the Data Center that talks about this. It's like 100 pages. It's written by Dinesh Dutt. The co-author of the VXLAN RFC. He helped invent Trill. He helped invent Fabric Pap. You can go download the free ebook from O'Reilly on our website. And it talks about exactly this. Highly recommend it. CumulusNetworks.com/BGP. If you're really lucky, there might be one or two copies floating around from your friendly neighborhood Cumulus folks in the back, but we might have run out today, so I'm not sure. Outside of telling you to RTFM, the way that this usually breaks down is that I'm going to have a single autonomous system number for all of my spines, and then I'm going to have an autonomous system number per rack, per set of leaves. And it actually turns out to be kind of important how I do this. So first, if I put one autonomous system number across all my leaves, what ends up happening is that BGP by default, eBGP, if I see my own ASN in a route advertisement, I drop it. So if my leaves are using the same ASN, I'm going to drop the route. And now all of a sudden rack 1 can't talk to rack 2. It works within a top of rack switch pair because they're connected to the same resources, and so I actually want you to drop that because I should have that connectivity locally. So on the leaf side, that becomes important. Otherwise, I black hole traffic and I lose connectivity between leaves. On the spine side, you have to share. Otherwise, you run into what's called Bgp Pap Hunting. And so Bgp Pap Hunting says, you know what? I know the route directly through this leaf, but I have a backup path that goes like that. It's not preferred because it's a longer path, but you know what? Through this like weird hip-hop mismatch, I've figured out how to reach that same link that just went down. So what's going to happen is this leaf here is going to lose its downstream interface and withdraw a route. I'm going to send a route withdraw up to the spine. The spine's going to go, no problem, I got this. You can actually come through me to reach the link that you just lost, because I have this incorrect and wrong route. And that will live there for just a moment until the leaf goes, wait a second, that's wrong, withdraw it. And we'll continue to go through this oscillation. It's what's called a count to infinity problem. If you've ever had the misfortune of studying for the CCIE and learning about like EIGRP site of origin, EIGRP site of origin is also a count to infinity problem where I keep oscillating my routing update between my MPLS edge and my MPLS backdoor link until it gets to the point where the number of hops in EIGRP, which you might not have realized there is a hop count in EIGRP not used for anything, hits infinity, and EIGRP goes, oh, this route's useless, throw it away. And then the network converges and stabilizes. BGP will actually do the exact same thing if you use unique ASNs per spine. You'll end up doing this BGP Pap Hunting, and the number of messages and the number of routes grows exponentially as you grow out that data center network. And it can be pretty problematic. And so it's really important to use the same ASN across those spines in an eBGP scenario. I would do a better job of describing path hunting, but it's just not going to happen. So RTFM. All right. Any other questions? Man, y'all are a lively bunch. This is like the third one of these today, and it's the quietest one, and there's even beer here. Like, get it together, guys. So the next thing that comes up frequently is, you know, when we think about VLANs and what do we use VLANs for and why do we have VLANs, VLANs tend to solve a few use cases. Number one is layer 2 extension. We've got some application that expects to be on the same wire as its peers. So a database cluster, sometimes other database clusters. But a lot of times they're using L2 for replication for these kinds of things. And they're not, you know, it's a poorly written application. It's not using multicast. It can't do L3. It can't do auto service discovery. And so it uses L2 for that or L2 multicast, and so I have to provision a VLAN for it. The other super common reason for VLANs is how do I get traffic from server A to server B and to the firewall. So I'll have a set of servers that are different tenants. And for the black tenant and the orange tenant to speak to one another, they have to go through a firewall, some sort of policy device. And so what I'll do is make the gateway for those servers the firewall. You know, sometimes we call this like, who owns the IP? Is the IP on the SVI or is the IP on the firewall? Right? Where am I putting the gateway for those servers in that subnet? And so I'm using VLANs to allow these two servers to exist within a rack or even within a pair of racks, but force the traffic to go out and back to get between them. Super common reason for layer 2. So the solution to this is EVPN. And so EVPN kind of becomes the solution. You know, I've started to say, like, look, EVPN is your answer. Tell me what your problem is. And the reason why is, again, it can do L2 extension, L3 extension, and L3 multi-tenancy, almost exactly like MPLS. And so what L3 VPN can do, I'm sorry, I'm giving away the lead. What EVPN can do is act exactly like L3 VPN MPLS. So I erase everything. So I create VRS to isolate my tenants. And so now I have two VRFs that isolate those tenants, and I can look at the firewall as the point in the network in which those VRFs come back together. So through simple routing protocols and routing advertisements. And now, from a packet flow perspective, if I have, I'm going to add one more server here. If I have two servers in the same rack that want to talk to each other, I would go through my top of rack switch and speak locally. Local bridging or local routing within that VRF, L2 or L3. Let's say it's L2 extension for that tenant. Well, what's going to happen is I'm going to come to my local top of rack. The destination MAC address is going to be for server 2. That top of rack switch is going to say, oh, this isn't for me. This destination MAC matches server 2. I learned that MAC address through EVPN, which means I have to wrap it in VXLAN. So EVPN is the messaging, the who, what, where. VXLAN is the how. It's the encapsulation of the packet or the frame to actually get it over there. So I'm going to wrap that packet as it comes up into VXLAN, send it to the remote leaf, who will then bridge it down to that remote server. If server 1 wants to talk to server 3, so I'm going between tenants now. Again, I'll send to my top of rack switch, and that top of rack switch will go, you know what, I do have a route through that, and it's through the firewall. So let me route you towards the firewall, again, through VXLAN, and I'll come out of VXLAN on the switch the firewall is connected to, so I can come in through the black side of the firewall. The firewall can apply its policy, and then I can come back down and route to that tenant. And so once again, EVPN becomes the solution for all problems. L2, L3, multi-tenancy, tenant isolation. So one of the things that came up when I was talking about this earlier today was, look, we've had MPLS forever. It does this. I've also got GRE, does this at layer 3. What's special and unique about VXLAN? What's special and unique about VXLAN is, one, the control plane, that ability to advertise that information and make it dynamic. You know, like one of the challenges with GRE is there's no routing protocol to tell me a GRE endpoint. You know, Cisco made $1 billion off of DMVPN because they just told me where a GRE endpoint was. And if you haven't been exposed to DMVPN, you're real lucky. And so the big difference is if I look at MPLS or I look at GRE, they don't have a layer 4 header in that packet, and that becomes really important. So MPLS has an ether type of MPLS, a label, and then the thing that I'm encapsulating. GRE has an ether type of IP. It has a source and a dest IP address of the two GRE endpoints, and then the thing I'm encapsulating. VXLAN, on the other hand, has an ether type of IP, a source and a dest IP address of the two endpoints of VXLAN. And this is what's really, really important, is it is a UDP packet with source and dest ports. The dest port here is VXLAN, but the source port is actually dynamically generated from every packet that gets VXLAN encapsulated. So as a packet comes into the top of rack switch, whether it's L2 or L3, packet frame, you know, be pedantic if you'd like, but as something comes into that top of rack switch, I'm going to run a hash across it, and that hash becomes my source IP. Every packet in the flow between two endpoints will have the same hash. Every packet in the second flow between those two endpoints will have a different hash, or could have a different hash. And this becomes really, really important in these spine and leaf networks. And so if we go back to this one, yeah, I love this little app. If we go back to this, what ends up happening is as a frame or a packet comes in here, I'm going to look at that packet, whether it's MPLS, whether it's GRE, whether it's VXLAN, And I have to figure out which of those 3 links do I send that packet over. And I do that using Ecmp hashing, equal cost multi-path hashing. So the switch itself is going to look at that final packet and make a decision. And it's going to pick a link and send the packet along that link. And every packet that looks identical to that packet is going to go over the same link. Well, in GRE, there's a source and a destination IP address and nothing else. So every packet looks exactly the same. In MPLS, I have a source and a destination address that are the same. And I have an MPLS label that's usually going to be the same. So every packet uses the same link. In VXLAN, because I have that UDP header, I have a piece of entropy. I have something that's changing between each of these flows. So when I go to hash, I'll send the DB1 to DB02 traffic over the first link, and the DB01 to web traffic over the third link. And now I could actually start to get efficiency in hashing across that environment. And if we step way back to our conversation about that really, really old school architecture where I'm forwarding on half and blocking on half, even if I wasn't, part of that is because layer 2 can only use a single path. I cannot multipath this traffic. But now, because I have the ability to hash even my layer 2 traffic, because it's encapsulated in something that is layer 3 and hashable, I can use every single link, whether it's 1 link, 2 links, or 16 links. And that's actually a really, really key differentiator for VXLAN in these data centers. So I can just never think about QoS again, never think about buffers, never think about anything, and just throw a shit ton of bandwidth at the problem. I can put 600 gig spines and never ever look at another bandwidth graph in my life because it's all hashing and beautiful and amazing. Questions, thoughts, comments?
So have you ever what's the problem with running to an organization that maybe running in like a traditional model or maybe like a fabric that spawn out of paper? What sort of problems have you seen?
So what problems have we seen is for customers running L2 or Trill or Fabric Path moving to this model? There are 2 big problems. And the first one, I say this a little tongue-in-cheek, but it's super honest, is they get totally sucked into that problematic tire fire that they can never actually get here. You spend so much time firefighting that you can never make the good. And so you're like, cool, we did the POC, we finally completed the POC, and then everything melted down, and then we had a change freeze, and then all of a sudden it's like 8 months later, and we've never actually rack and stacked that gear. That is absolutely the #1 thing. And I do think that at some level, whether it's your management or it's your executive leadership, you have to have a little bit of air cover to like, no, this is the bad old, and that is how it is. We need that space to move forward and do something else. So that's the #1 problem is organizations that just don't allow their people to fix it. #2 is it is a different way of doing things, and you get very used to how to troubleshoot and that methodology and that mentality, and it is different. And it is a little complicated, to be perfectly honest. And so it's hard to make that shift. And for that, to grease those skids, you have to look at things like VMs and virtualization. And I don't mean like NFV and OpenStack, but I mean like GNS3 is a bad example. Apologize for another sales pitch, but we make a VM called Cumulus VX, and it's fully featured, right? We support VLANs, VXLAN, L2, L3, ACLs, you name it. Everything we do, we make work in the Linux kernel first, and then we push it to hardware. So if I remove the hardware, and I just have the Linux kernel for a testing VM, well, then I have a switch. And so that means that I can build my whole data center out of these VMs, and any vendor should be able to do this for you. They just generally choose not to. But I can build my whole data center out of these VMs, and now I can start troubleshooting. Because one of the biggest problems you have in troubleshooting is something's broken, and you see an output, and you're like, that's weird. You're like, wait, was it always weird? What is expected behavior? You don't even know because you've never chased down how to track a Mac through EVPN before. It just didn't work all of a sudden. You're like, I don't understand this output. It must be the reason. And then you call support, and everything's the worst. And so if I have an environment that mirrors production, I can actually study through that environment. I can look at those outputs. I can look at those commands and say, like, what is steady state? What is expected behavior? What do I think this should do? I can hire somebody on and be like, here's your vagrant file to stand up the whole data center on your laptop. Go learn how we do things and report back. Instead of being like, here's your read-only SSH access. Please, for the love of God, don't run a show tech because we have that bug where it crashes when you run a show tech. We've all done it. You know, the best part about being a TAC engineer is when the show tech crashes, the box bug comes out, and then the customer opens a case, and you're like, yeah, just give me a show tech. Son of a bitch. That's always. That is actually, that we've. One of my favorite bugs that I filed, they left the GDB, the C GDB debugger enabled on the box, but it was a hidden command, so nobody noticed. And so if you typed G space K enter, the box would crash because it was GDB debug kernel, and it would lock up the CPU and the box would crash. And so G space K, some 12.4 code for a good time. Look, I'm not trying to vendor bash. We have bugs. But to me, a lot of this is like, look, everything's awful, and it's always going to be awful, and it's really complex, hard software to make. How do I, as an operator, make myself more reliable and efficient? But it's a very long-winded answer is, look, you have to have air cover to be able to make the change, and you have to have a way to be able to operationalize it that's successful, because otherwise we're always living 2 weeks behind schedule when it comes to tickets and projects, best case scenario. And so how do I actually understand what's going on and what's happening and what I should expect in my environment? And I think that we always miss the fact that we don't understand expected behavior. So those are usually the challenges that I see. Any other questions? Yeah, so DCI, best practices in this topology. So the first thing that you're going to do is you're going to go, cool, we're VMware shop. I want a vMotion between data centers because that's awesome. Don't. I mean, look, the reality is we're all going to do it anyway, but like most of us are not running hot data centers with L2. We want it for DR, and like if you're doing hot data centers, you're doing it through global load balancing or something else, in which I'm redirecting traffic into a data center, and then once it's in that data center, it lives there. Because otherwise, what you're really saying is I want you to be able to come in through Las Vegas, backhaul over level 3 to Herndon, and then actually access the server in Herndon, which then has to come all the way back through Vegas to go out to the internet because it's a stateful firewall there. And nobody actually wants to do that. So that's gripe number 1 and why you shouldn't do this. Gripe number 2 and why you shouldn't do this is you go, no, we don't do that. We don't do hot data centers with L2. We're better than that. And you go, this is for disaster recovery because we need business continuity. We're smart, we're thinkers. And then you go, well, what is a disaster? And you're like, oh, well, we'd lose the data center. Fuck you, vMotion, if you lost the data center. Right? Like, there's a whole nother set of problems there. So now you're back at cold restart anyway. Whether or not you can sell that to management, whole other problem that I can't help you with. But from a technical perspective, I think it was Ivan Teplaniak had something recently, the iOS hints and tips guy, IP Space blog, who was talking about the fallacy of the L2 DCI, because either you're going to blow your foot off when you melt down, like why melt down one data center with L2 when you can melt down 2 data centers with L2? Or you're going to trombone traffic, and you're just going to completely congest your terrible high latency link between DCI. Or number 3, you think that it's there, and you think somebody's holding the ladder, and there is no ladder. Because your data center went down, and so your DR plan was to vMotion everything else, and the only thing that actually ever really works for is if you lose all 4 of your redundant internet connections out to your 2 providers. In that one failure case, if you are smart enough to allow management backdoor in through the other data center, or you have a 3G card that allows you to get to remote access to actually execute the vMotion, which, I'll put $10 on the table that says most of you don't. So with all that said, the first way to do DCI at layer 3, hopefully, is, again, spine and leaf, all the things. And then we generally, you can connect them to the spines, but generally we're going to create a couple of devices called exit leafs, or service leafs they're sometimes called. Border leafs they're also called. Depending on your scale, kind of determines how much of this you're going to do. And so out here, off these exit leafs, you're going to put your WAN connectivity. This is also where you're going to hang your firewalls, your load balancers, any sort of middle box are going to hang off of those exit leafs. This also makes it much easier to, if you have to do VLAN provisioning to get, say, VLAN outside, firewall, VLAN inside, that becomes way, way easier if it's all in the same rack. And so generally, you're going to do it through exit leafs like that. And you're going to do it at L3. And then if you really, really need to, and you hate freedom, you can do EVPN between those data centers and extend that L2. And then you should feel bad every night you go to bed. Just like whisper to myself, I'm bad at this. This is not my fault. By the way, did I mention that I sometimes have opinions and I share them?
It's very funny when you share.
Oh, that's good. Okay, thank you, thank you. But in general, though, we're going to have exit leafs or service leafs, and I'm going to bring those attachments in. The other thing that's really important about bringing those in to leafs and not to spines, a lot of times is one, what is the cost per port? So if this is a 32 by 100 gig spine, these are 48 by 10 gig leafs, and I have a 10 gig internet connection, do I want to burn a 100 gig port for that 10 gig internet connection? Probably not. So the cost per port is much higher. But the other thing is when level 3 does the thing that level 3 does, and your port just starts flapping every 15 seconds, do you want that to drive up the CPU and take down a spine? Or do you want it to drive up the CPU and take down an exit leaf? I'm going to vote for the exit leaf every day. Because I at least still have all of my intra data center connectivity working, and I've just lost that DCI point. Most people, it's not going to make financial sense to do multiple sets of exit leafs just because they're like, well, I've got 2 internet connections and a firewall and a load balancer, so I've got like 4 or 6 ports. I'm not going to buy 4 48-port switches to accomplish that. So they will double up, but for larger organizations, you actually might look at a pair of exit leafs for the internet. So you have one set of exit leafs to get out of the data center for DCI, and those middle boxes are services, and another set of exit leafs to get out to the internet. And again, it's just about trying to collapse down that blast radius. So when really bad things happen, what are the consequences of those really bad things? And even in EVPN, you know, I think it's easy, whether I'm up here talking or you're listening to any of the vendors talk about EVPN, it sounds like really magic pixie dust stuff that solves all the world's problems and like layer 2 will never be a problem. But we're still talking about layer 2 at some point. If I have a server down here and I misconfigure that server that instead of a bond, I make it a bridge, I just melted down 2 data centers if I'm doing L2 extension here. Because EVPN doesn't change the semantics of layer 2. That packet is still going to go out, come around, and create a loop. And I still have to flood and learn to some extent. There's a lot of flood reduction and broadcast reduction, especially around ARP. ARP is usually the culprit in a lot of these broadcast storms because most hosts don't send broadcasts that aren't ARP packets. Well, let's say I send a multicast frame in a looped environment. So EVPN is usually implemented in which the top of rack switch will be like, you know what, ARP is special. I'm going to grab it, I'm going to throw it away, and I'm just going to reply locally because I know where all the remote devices are. And if I don't know, then it doesn't exist. But if it's a multicast frame and I have to flood that multicast frame to all of the VTEPs that have this VLAN, that is the exact same problem, and I've just flooded that multicast frame everywhere. So EVPN does not eliminate the terror that is layer 2. Hide your kids, hide your wife. Exactly. So let's talk about the networking panacea, the top of the mountain. And so the top of the mountain is BGP on the host. So what I do is, again, I take my leafs, and I take my server, and I have my 2 links. And instead of building a bond, which I've always done, and instead of assigning an IP to this bond, I'm not going to do any of that. I'm going to run 2 eBGP peerings to those top of rack switches. And I'm going to use that same BGP unnumbered, so I'm not assigning IPs to every one of those server links. And you know what? If I actually like work in an organization with money, because none of us do. And I have something like NVMe drives that can push like 100 gig out of a host. I can attach to more than 2 leafs if I need to now. Where before I'm limited by MLAG and I can't do that. But you know, although this is the top of the mountain, that's a little bit too made up even for me. So I'm going to do 2 BGP peerings out of this device. And what I'm going to use on it is I'm going to put an IP address on the loopback IP of a /32. And that /32 is going to get advertised out into the environment. And this becomes the IP address that I bind my services to, that I put my Nginx cluster on, that I have Apache listen to. And now I get a couple of really incredible things as a result. One, I never have another layer 2 anything, because I don't even have a VLAN here. The port to my server is routed. Nowhere in my environment is a layer 2 domain larger than a single link. Not even 2 links in a bond, it is exactly 1 link on every single device in my environment. Pretty remarkable. Number 2, I can do 0 packet loss upgrades across my network, and I never have to call my server team. Because every time we take down one of the top of rack switch pairs, you know, you sacrifice the chicken, you cast some bones, you rub your rosary, and you really hope for the best, and you still fuck up VPC. That's like, it's what happens. Reality's a bitch. So you end up taking down that server cluster. And even the fact that risk exists means that you have to tightly coordinate with your server teams to do any maintenance on your network. And so we end up running 20-year-old code because God forbid we ever take down a top of rack switch. But what if I didn't need the server team to do that? What if I could automatically, through the software, tell the server I'm going to go out of service? I mean, this is routing. That is exactly what routing protocols do. They tell directly connected or indirectly connected devices, don't use me, or I'm less preferred. So I can come in and I can advertise an AS path prepend out of that top of rack switch. So now all of a sudden, instead of having 2 equal cost paths, that server was just told it only has 1 optimal path and 1 path it shouldn't use. And I can sit and then just look at my interface counters to see when that routing table on that server has updated. And when my interface counters on my maintenance switch go to 0, because the server's fully moved over to only routing on the other device, I can now do my maintenance. I can take it down, I can reboot it, I can do whatever I need. I can run a show tech on the device if I need to. And then when I'm done, I remove the AS path prepend, and the server relearns 2 equal routes and reinstalls them and everything's hunky-dory like it never happened. And I never had to call a server person. And then I take this a step further where I can start to automate this process. Because our data centers look pretty uniform, in which I've got a bunch of top of rack leaves, and I can say, well, this is the A leaves, and these are the B leaves. And now I can put them in groups and roll across with a tool like Ansible and say, look, on all the A leaves, do a path prepend. And now wait for all the A leaves to have all their traffic drained. And then on all the A leaves, do a software upgrade and reboot. And then on all the A leaves, bring them back up and remove the path prepend. And now when everything's stable, do the same thing to the B leaves. And we have customers doing this. I've seen this in production. I saw a customer do an upgrade of, we did this on a chassis, actually. It was 4 chassis in a lab. So it's 4 line cards that look exactly like this with 4 spines. 0 packet loss and plugged into Ixia in something like 5 or 10 minutes to upgrade 12 instances of software. So you can't shut down VPC in 12 minutes. I mean, you can. Anything can be shut down with the big red button. Well, it all depends. So the thing is if you drop the link, in theory, BGP should immediately converge because it saw a loss of signal. In theory. The one thing is even if that happens instantaneously, you're still going to lose everything in flight. Maybe that doesn't matter because it's like, I don't know, like 2K worth of data. But, you know, if I want to avoid that situation, I can just this is like a more graceful shutdown method. You could be as mean to your server people. I mean, and to me, to be perfectly honest, we as network providers should act as an ISP, but slightly better, in which you say, here's your SLA, here's what I can guarantee you, you figure out what you need. And so I should have the ability to do exactly what you're saying, which is just nuke a leaf, and that's not my problem. Their application to respond to that, I don't care about that, you know, 30K in flight, and they should be updated enough to be able to respond. But, you know, the world doesn't really look like that, unfortunately.
So now, what is that? So does it mean that on each VM I need to run some type of routing engine for that to work?
You also took a question out of the question jar. So the question was, for those that couldn't hear, I work in the enterprise, I run Windows, I call bullshit. Is that a fair assessment? So, number one, Windows has a BGP daemon built into Windows Server. So if you run Windows, this is actually pretty easy. If you run Linux, our routing application, free-range routing, used to be called Quagga before we made a bunch of updates and forked it with some other folks. You know, it's what James said. You can go pull the open source version, or you can pay us for support and run it directly on your Linux servers. Because we're Debian-based, you can run our exact package we run on our switch. Literally the same bits, the same bugs, the same support configuration on Debian, Ubuntu, or Red Hat. For VMware, VMware is a super special case because unlike KVM, which is the other major hypervisor out there, KVM is a hypervisor running on Linux. So I log into a Linux server, it's a full-blown Linux server, and it's also a hypervisor. ESX, you don't log into it. Like it's a closed system, right? I don't log into Windows to then get to the VMware ESX. ESX is the operating system. So you cannot do this in ESX easily. You have two options. Number one is exactly what you stated. And we have a customer doing that where every VM runs BGP. And so my pizza box switch has like 240 BGP peers. That to me is extreme. I mean, awesome, because I love this solution. But I also am pragmatic enough to recognize that doesn't work for anybody but them. So the other option here, we have a feature called redistribute neighbor. Arista has something similar. I think they call it redistribute ARP. But basically, when a /32 shows up on that leaf via an ARP entry, so it ARPs out for its top of rack switch, I turn that /32 route into a BGP update. So I'm redistributing my ARP table into my BGP table. So ESX, the VM, they don't run any routing. They're not doing anything special. They're pointing to the top of rack as a default gateway, and that's it. And then the top of rack gateway is taking that ARP entry, creating a /32 route, putting that /32 route in BGP, and telling everybody else in the world about it. So that gets you like 80% of the routing on the host functionality. But now you don't need a BGP daemon directly on that server.
So in large enterprise, networking systems use two different daemons, right? Hierarchy. How do you prove the money total and server to say like /24 or you get to like two cats? From that perspective, so how do you, I mean, is there any enterprise when Windows Chronic gathers that
So there's two questions I'm going to tackle separately. Number one, keep me honest here. Number one, is there anybody in the traditional classic enterprise where we're highly siloed doing anything like this? Number two, and I'm paraphrasing, I work in an enterprise and everything is terrible, please help. Is that accurate? So for number one, the only way you get there is through process and policy. And it is super hard and super time consuming, and I think for most it's not worth it. Because the marginal gain here over just doing EVPN and terminating on a firewall or having an anycast gateway at the top of rack switch, it's going to take so much work to get there to define the process and policy for what those server folks are going to have to adhere to that, like, I don't even care that much. So I'm not aware of anybody in a traditional enterprise that is that siloed doing this. I have, however, seen, you know, some of the largest, like, financial institutions of the world who are just as siloed as any terrible enterprise say, like, everything is terrible and we have to do better, and so, like, let's start making baby steps. Can we run routing on the host for ChemTech, but recognize everything else is going to be EVPN? Because even in that EVPN scenario, I could do routing on the host and EVPN simultaneously, and the switch doesn't care. It's just another way it got a route. And so they'll pick and choose those applications and allow the server team to realize this is a better way of doing things, and if we can move there, that would be awesome. Or you jump on to new projects and capabilities. So whether it's a Docker deployment or an OpenStack deployment or a Mesos deployment, and say, look, the way that you're going to be able to plug into my OpenStack network is with routing on the host. And if you don't want to use routing on the host, go build your own network. And they're going to buy like 6 Linksys switches, and it's not going to work. The second part, I work in an enterprise and everything is terrible. You're not alone. This is the same conversation everybody has. Like, this sounds amazing. How do I get there? How do I do this? I don't understand. They don't speak my language. I don't speak theirs. And I think the only thing we really can do as engineers, especially as network engineers, is little victories and being able to concretely demonstrate value and wins. So a simple example would be automation, right? I work with a bunch of slubs. They don't want to learn automation. They don't want to learn Ansible. Why should I learn? We can't get anywhere with it. And then guess what? Daylight savings time changes because that was the politically correct thing to do and it won Congress votes. And your software doesn't update to the fact that daylight savings falls on a different day of the week now. And so you have to manually log into every device in your network. And so what you did, because you're smart and you want little wins, is you changed the time zone on every device in your entire network using Ansible. You're not managing config. You're not trying to boil the ocean. You're not trying to solve world hunger. You found one little win, and you took 12 hours of work down to 40 minutes, and you can be like, hey, look at this thing that I did that took 40 minutes. Isn't that super cool? And then somebody accidentally posts the full show run with the enable password on pastebin, and you're like, oh, damn it, now we have to change the enable password on all the devices, and that becomes your second win. And all of a sudden, people are like, you know, this Ansible thing is kind of cool. There's no way we're ever going to let it manage config, but now we'll actually entertain the idea and not burn you with a stake as a witch. And so you start to make these little wins and get further along. And then you hear these conversations in the hallway about the server team running Ansible, and you're like, wait, we're starting to speak the same language. And then you start to build trust or ask questions. And now all of a sudden you trust one another enough to be like, hey, so how does this Oracle database work? Like, I'm super dumb here, but I'm going to go out on a limb, and I want you to talk to me about how this Oracle thing clusters. And then you start explaining it, and you go, oh my God, I understand this. It's using an L2 multicast frame, and it's expecting L2 extension with multicast, and that's why IGMP snooping broke, and that's why we had that ticket 6 months ago. Okay, I understand this now. And now, when I make future updates, I have a better understanding of a requirement that they didn't even know they had, and you can be a better provider. And the reality is it's political capital that takes a ton of time to build, and it's a hard grind. And the only way that you accelerate that is with basically somebody at the top coming in with a stick and hitting everybody that doesn't get in line. And those people generally don't last very long. You know, so outside of that, the only place that I've seen rapid adoption is existential crisis, to be perfectly honest. And that's also a shitty place to be. in which you have your company provides a service or something where IT is such a core value that you've neglected for so long that continuing to neglect that service, whether it's the network or IT in general, now jeopardizes the core business of the company. And so you have this existential crisis where it's either perform better or we're effed, either as a company or as an organization. I think AWS has been great at that because I think a lot of development sides of houses are saying, well, I can either go to the infrastructure folks, not just network, but compute as well, and say, I can go to infrastructure and ask for a VM and take 4 days, or I can swipe my credit card and expense it in 15 minutes. And then all of a sudden, the shadow IT that was AWS grows and grows, and now it's a thing, and now there are directors and VPs on the development side that are behind it, and either infrastructure figures out how to get their house in order, and again, that is compute, that is network, that is storage. We're not alone here. We either get our house in order and able to allow for self-service and turnkey, or we lose our jobs, right? Or we become AWS admins. And I mean, that's an extreme way of putting it, and that's still years down the road for a lot of organizations. But that existential crisis, when I see directors and I see vice presidents see that existential crisis coming, that's when I tend to see the most productivity coming out of organizations, where they're like, no, whatever it takes, we're going to break down the walls, we're going to figure out how to make OpenStack work, we're going to spend a little bit of money with Red Hat to make it work, we're going to build a better network, and you know what? That's how we're going to do this and fight back against AWS. And if we fail, then, you know, like, update LinkedIn.
We find on the Linux side that you get our ranking so good, but when it gets to Windows.
Yeah, and I think, and again, so one of the things you can do there is just build pods around it, right? So you say, this is my Windows pod. It's 6, 8, 10, 12 leaves. You can find smaller form factor switches to build. You know, if we go back to a 3-tier CLOS, somewhere in here, you can have a Windows pod and basically be this is the scary basement that nobody goes into, and this is where all the Windows machines are, and you can deploy a Windows machine anywhere within that pod, and it'll work, and it'll do what you want, it'll meet SLAs and everything else. And then you know what we're going to do in every other pod? Good stuff. Not deploy Windows with L2 requirements. Yeah. Yeah, and I mean, that's a huge point in which, you know, chargebacks have never really worked but are the dream, because then I just charge you more for a Windows port than or routing on a host port, I charge you less than an L2 port, right? That would be ideal, but it's never going to work. What's going to work is that, look, if you want to run a Windows VM, I can give you a Windows VM in a limited capacity location that's going to take twice as long to provision, or I can give you, you know, a 512 meg Linux VM in 30 seconds. And you know what? They're going to make their stuff work in 512 megs. You know, and so you kind of lead the horse to the water and let it figure it out. But, you know, I think you have, again, your problems and your problem space is not unique. And so all you can really do is build a wall around it. Any other questions? No. You know, we have like the little rocket turtle is the Cumulus logo, and somebody jokingly made these "Make Networking Great Again" little rocket turtle stickers. And we ran out, like everybody's like, it's real funny. And then we ran out of stickers, and I've got a customer who's like, man, I want some of those stickers. I love those stickers. And it's like, I just can't do it, man. I can't do it. How are we on time? All right. Yeah, so anything else anybody wants to cover in the last few minutes before we drink another beer and sweat a little bit more in this air-conditioned-less office in the evening? Yeah.
I'm a Linux guy who's stuck into the network meetup, so.
It's all right. I was crashing the DevOps meetups here in Boston for years, and I'd be like, excuse me, I don't know who Jenkins is or why y'all are so interested in him, but I'd really like to meet him. So
anyway, when I was asked to talk a little bit about the relationship between VPN and VXLAN, in my super basic reading, it seemed like you could do the whole overlay network thing with just VXLAN. So what's the difference and how do they get it?
Yep. So the question is, what is the relationship between EVPN and VXLAN? So VXLAN is a tunneling mechanism. I can capture a VXLAN packet on the wire with TCP dump or Wireshark. And a VXLAN packet is IP in UDP in whatever the person sent you. So it's fully encapsulated IP and UDP. This thing is a VXLAN packet. So with VXLAN, let's say it's layer 2. So I have server 1 at 0 dead beef. And I have server 2 at 0 ace cafe as MAC addresses. And these two servers with their MAC addresses live behind 2 leafs. So the question is, how does leaf 1 learn about server 1? This happens through what's called conversational learning. So server 1 at some point is going to send a packet or a frame, and server 1 or leaf 1 is going to say, oh, server 1's plugged into this port I now know because it sent me a frame. But that frame never goes across this routed fabric. The whole concept is that the L2 framing stops here, and I only send routed fabric routed over. So what EVPN does is EVPN in an EVPN message says, I have 0 dead beef behind me. And so if you have anybody trying to reach dead beef, send it to L1 and I'll figure it out. It's merely a communication protocol. It relies on BGP. It's a BGP message. You can think of BGP as a distributed data store or a distributed database. And so I'm effectively putting in a specific type of record into this distributed database that shows up over on L2. And L2 now says, OK, cool, got it. And so then S2 sends a frame over to dead beef. And L2 says, where do I know dead beef? It's not attached. I learned it from an EVPN message that came across to me that said 0 dead beef is located at L1. So what I'm going to do is I'm going to build a VXLAN packet destined to L1, sourced from L2, and inside is that original frame. So the VXLAN is the packet. EVPN is the messaging, the control plane, as we would call it, about the who, what, where is EVPN. The how is VXLAN.
Is it fair to say that's kind of how the VTEPs, as we call them, learn about each other's tables?
Exactly right. That is exactly, so it is how the VTEPs learn about each other's tables. Yep. Yeah, you're.
Prior to EVP, things that broadcasters and all kinds of hashing multicast, broadcasting multicast things. And then EVPN came along and kind of helped facilitate the control aspect of distributed all these backgrounds.
Yeah, so in the traditional environment, to restate what James was saying, in a traditional environment where I have only conversational learning, if this is a layer 2 network, and we'll ignore the fact that there's multiple links, but if this is a layer 2 network, as that frame came in, I would have to flood that frame out every link, who would have to flood it out every link, who floods it out every link, because I need everybody in the environment to learn about that MAC address so anybody knows how to reach it. And so an EVPN scenario says, look, number 1, instead of flooding an actual data packet, I'm just going to send the database record. Number 2, if you don't have anybody that can ever talk to that server, I'm never going to send you that information anyway. And so we have this ability to prune away that data that's not relevant to that VTEP. Any other questions? Useful, not useful, boring, interesting? All right. Well, we weren't really sure how this was going to go. It's like the 3rd time I've had this conversation today, and I have no idea what's going on anymore. So thank you all. I really appreciate your time. I enjoyed this. I hope you all enjoyed this. Talk to James. You know, let's get BossNock going again. We clearly have a community. Let's keep it and let's grow it. And I'll hang out for a little while if you got anything else. Thanks, y'all.